Nice Monday. Okay. Here we go. All right. Welcome to Monday. Ready to get going again. Hope you had a nice long weekend. Okay. So these are some words for Elder Holland to get us ready to talk about brass instruments or lip reed instruments today. He says, now these mortal angels who come to this pulpit have each in his or her own way. Ready? Sounded the trump of God. Every sermon given is always by definition both a testimony of love and a warning, even as nature herself will testify with love and a warning in the last days. So I think it's interesting, especially as we're coming up on conference. Elder Holland gave another really good talk I listened to recently, where he basically was talking about how to listen to conference. Kind of interesting. And he was saying, you know, it's okay to recognize that not every talk is for you, you know, and it may or may not apply to you in your particular situation, right? But that to go with your questions in an open mind and then be able to feel the Lord's love through these wonderful people who share their messages. Okay, so today we get to talk about lip reed instruments. Okay. So by lip reed, we mean brass instruments, okay? And so we have Amber, who's going to help us with baritone, and Emma is going to help us with trumpet. Hopefully she's on her way. Okay. Everybody turn in their dosimeter? Any other dosimeters? Okay, we need lots more dosimeters. Okay, so just pass them to the end of the row so Elena can pick them up, please. Okay. Okay, so the first thing we're going to talk about with these lip reed instruments, like we do every day, is to identify the source of the excitation, the source of the oscillation, the filter or resonator, and the radiator. Okay. All right. So on your learning activity, you got to practice, right? Where was the energy coming from for these lip reed class? What was producing the energy? Your air, right? Similar to all of these wind instruments, it's your air. And then what was doing the oscillating? What was breaking that steady stream of air into puffs of air? The lips, right? And so the lips were performing the same role as the mechanical reed and the vocal folds. So that's why this chapter is called lip reed, because the lip is playing that role, okay? And then what is the filter or resonator? What determines which notes you can actually play? Like, can you do a ooh like that on a brass instrument? Okay, so what determines which notes you can play? What is resonating? Yeah.
The length of the tube and also the speed of your air.
That's right, the length of the tube and then the speed of your air. Okay, but the length of the tube is the resonator here. Okay, and then the radiator, where is the sound coming from on these instruments? The bell in all of the cases. Okay, so those are the answers so that you can make sure you have them written down correctly. Blown air, and then the lips vibrating to match the resonances of the length of the tubing, and then the bell is the radiator. It's where the sound is coming from. Okay, so here are some examples that we'll talk about. Hopefully today we'll get to see a trumpet and a baritone, and then there's the tuba, the French horn, and the trombone. So those are the ones we're thinking about today. Okay, so now we're going to convince you that that this is doing exactly what your vocal folds are doing, okay? So this is the video of a trombone player's lips. Okay, so they drilled a little hole and put a little camera right in by the mouthpiece so that they could get a video of what the trombone player's lips were doing. Okay. So, little hole there, they can put the camera in. Doesn't that look an awful lot like the vocal folds? Obviously, this is under strobe, so you can see it vibrating, right? That's exactly what the vocal folds do, right? I mean, this is the top lip doesn't move as much as the bottom. The vocal folds are more symmetric. Okay. That's a higher note, right? So similar to the vocal folds, you got longer, right? Less open. Louder, you have a wider amplitude, right? A bigger opening to play louder. Higher note, right? And notice how they don't close all the way like the vocal folds on those high ones. Once you play louder, right? You have a bigger displacement amplitude. Okay, are you convinced? That kind of an interesting video. Okay, so that's why we call them lip reads, because the lips are doing exactly what the reeds are doing. Okay, so then there's this comparison with the voice. I'm not going to read through all of this, but it's in the slides if you want it, okay? But it's this idea that the lips for these lip reed instruments are doing the same thing as the vocal folds. But the difference is the lips, right? And the vocal folds are under our control, right? There's something you're controlling. The lips more consciously, the vocal folds well, I mean, you are consciously doing it, but you shouldn't think about it. I don't know how to count or how you call that. But sound comes from a single opening, okay? And you have this kind of periodic motion. So if you have periodic motion, periodic airflow, what's the spectrum going to have? All the harmonic partials, right? Because that's by definition what a periodic wave has. Okay, but the difference is that, again, the vocal folds and the vocal tract are not coupled. That means for any valve sound, any vocal tract configuration, you can do any pitch. Okay, but there is a coupling between the resonator of the tubing and the lips, okay? It's not as strong as on the clarinet and the mechanical reed instruments, which is why you can bend notes more. We'll see examples of that, but that's what we're doing. Okay. Okay. All right, this was our summary table. We're on this lip reed column now, okay? The lip reed will have the fundamental frequency and all of the harmonics. This is, again, not because, well, it is basically closed open end, like the clarinet or the vocal folds, but, or, you know, vocal tract, but it's more cylindrical and it has a bell, which make it have all the harmonics. So the clarinet is the only one we will say has only the odd harmonics. Okay. Now this is another really interesting demonstration. Okay, the idea is that all of these lip reed or brass instruments, almost all of them, are scaled versions of each other. Okay, meaning the excitation and the oscillation, the source is the same, right? The resonator is the tubing, but if you have shorter or longer tubing, then you will have different octaves, essentially. You'll have different ranges for these. So what this picture is showing here is the relative sound level, like the spectrum. Okay, so this is an envelope of the spectrum, average spectrum for a trumpet between 400 and 4,000 hertz, the trombone between 200 and 2,000, and the tuba between 100 and 1,000. So it's kind of like the, you know, if you double the length of everything in the trumpet, you almost have the trombone. If you double the length of everything in the trombone, you almost have tuba. They have this similar spectral qualities, okay? And we have an audio demonstration for you to hear that. Now, remember that frequency and time are inversely related, right? So if you have a trumpet and you slow it down, that's the same as taking it to a lower pitch. If you have a tuba and you speed it up, that's the same as taking it to a higher pitch. All right, let's go ahead and listen to this.
My name is Mildred Austin. This is the project I'm turning in for Physics 167, spring semester 1969. The basic recording of these samples were made at as many as 3 different tempos, so that when they were re-recorded at greater and lesser speeds, the tempos would be the same for each comparison. The first comparison will be as follows. The trumpet will be played as originally recorded. Then the trombone will be played re-recorded at twice the speed of the original. Then the tuba will be re-recorded at 4 times the speed of the original.
Okay, so does that make sense? They play the trumpet, regular tempo, the trombone, half speed is how it was played and recorded, so then you could double the speed on the recording. And the tuba was played 1/4 the original speed, so they could do the recording 4 times faster. Yeah,
Like it's all the same piece.
yes, it's the same music. They just played it, they recorded them playing at different speeds, so that when they all are the same speed, the frequencies of the trombone and the tuba get shifted higher because the times are all short. Any other questions about that? So that's the regular trumpet. Now this is the trombone sped up by a factor of 2. And this is the tuba sped up by a factor of 4. Okay, they're just scaled models, right? The tuba sounded maybe like it was a little muted, right? It has, the spectral qualities are a little bit different. Right, if we look at this picture again, there's a little bit difference, right? But in general, because they have the same shape to their spectrum, if you would modify the tempo, you will get the different, they will begin to sound similar. Okay. Questions about that? Okay, so there's a factor of 2 between the trumpet and the trombone, and a factor of 2 between the trombone and the tuba. Okay, so if you wanted to make the trumpet sound like the tuba, what would you do to the trumpet? You'd slow it down by 4. By a factor of 4, you'd have it go a quarter as fast, and that would make 400 hertz sound like 100 hertz, and 4,000 like 1,000.
So is this saying that like, how to phrase, I can't remember. Like the trombone plays like an octave lower than a trumpet, and a tuba plays an octave lower than a trombone because the ratio is 2 to 1.
Exactly. They're kind of like main playing range. Is that exactly that, separated by octaves? Okay. Good. Questions about that? All right. So we're going to start with a little trombone demo, okay? And I don't have a trombone player today, but I'm going to pretend that I'm the trombone player today. And we're going to do a garden hose trombone, okay? So that we can look at the spectrum. So here's my tubing, right? Okay. And then if I buzz my lips in a tubing, there it goes, right? I'm going to do it a little quieter. You see how when I did it quieter, the fundamental and 3 times the fundamental were louder than the 2 times the fundamental. So that open closed tube model is almost okay for a cylindrical, right? Just a even cross section and buzzing your lips. Okay, and then I'm going to get louder. Oh, okay. So you can see the amount of partials, and I shifted my pitch a little bit. There's a little bit. Okay, but now the question is, what happens? Okay, so what happens when we put on a bell? Well, first I'll do a different one. I'll try. See if I can do this language. This is a much longer tube, right? But I can hit different notes, right? Right, based on the precious. That was a lot harder to play. So I'm going to go back to this one. Okay, we're going to look at what happens. Well, first, I'll try to play different notes. this is painful to listen. We're gonna listen to the. But I want you to see now what happens when I have a bell. See, in most of those, 1 and then 3 was the next price. But if I add a bell. Good. See all those harmonics? Yeah, before it only was a tenthful and now it goes all the way up. Okay. So bells, that's what bells do. And then I can have different shapes of bells. All those different shapes. And then I can add a mouthpiece. So let's see what the mouthpiece does. Okay. Like I said, it again changes the spectrum. This one doesn't fit completely, so that's why it gives that extra noisy background. All right, so that's just kind of your intro, the pieces, right? In a not elegant way. Okay, so what does a bell do? You saw it. What does it do?
Harmonic.
It increases the amount of the upper partials, the higher partials, and it makes it so there are all the partials instead of just the odd and soft. Yes, so I think it's. I will switch back over here. So you can see. These are the things that the bell does. Makes it louder and clearer, better sound radiation. It changes the fundamental a little bit because it makes it longer. Okay, you get all of the harmonics, and then it introduces a cutoff frequency. This is what I just- Okay, so let's go ahead and answer where are these questions. Save those questions. Kind of jumping all around. We'll make sure we get to them. Okay, so Emma, say anything. I'm just gonna. Okay. I've done all the buzzing my lips to do today. So really demonstrate for us all of these things. Okay, so while she's getting ready, let's do question number 1. Okay, this is the trombone part of this question. Trombone produces all harmonics because of what? What makes it so that all of those harmonics are nice and bright? See. It really is an open closed tree, but it's the bell and then the fact that it's we have a conical bell and something shaped. Okay, number 2 we already talked about also. Okay, this is that idea of coupling, which the reed motion. Yes, sorry, please.
What does it mean that the bell flattens the higher partials?
So instead of them being 2 F1 apart, it kind of makes them so they're just 1 F1 apart. Is that your same question? Okay, good. Then Roman numeral number 2, okay, treating the vocal folds as a reed and the lips as a reed. The voice is the least coupled, vocal folds and vocal tract are least coupled, meaning you can do any note with any vocal tract configuration, any tube configuration. The lip roots are kind of in the middle. You can't play every note. You can't do a glissando with one G-link, but you can bend them. And the mechanical reeds are the most custom. Like that's why the clarinet screws. It's because if you don't match the vibration of your lips to and the reed to, or sorry, the vibration of the reed to the resonance of the tube. It dictates the reed, the tube dictates the frequency that which you can get. Questions about that? Okay, now we have a trumpet. Okay, why don't you come over here and play your trumpet?
Played my trumpet for like 2 months.
That's
so-
okay. Just single, okay, so first, why don't you show us or tell us, how do you change notes on the trumpet?
So changing notes is just all you do with your lips, basically it's just tightening like the corners and then loosening that helps make your lips looser in the mouthpiece. You can also shift your lips around, so that's what it.
So for a single tube length, it's your mouth that changes. Okay, so why don't you just choose one tuning, whatever you prefer, and then go ahead and just play like your lowest note and then work your way up the partials. Okay, so look at those stair steps. Do those stair steps look like the same distance as the first note you wrote? Or are they like half that distance? You can tell they're half because see there's, for this note, that's F1, 2, F1, 3, F1, 4, F1, 5, F1. But then when she went to the next partial, it wasn't the same as an octave above. Okay? And that's because typically with these brass instruments, you never play, hardly ever, the lowest note it can actually play. Go ahead, can you get that one? So it's kind of, they call them pedal tones, right? And they're not as nice sounding usually, okay? But then after that, these jumps, right? They're going up by even spacing. That spacing is F1. So this would be say 2F1, 3F1, 4F1, 5F1, 6F1. Right? 2F1 would be the octave above. When's the next octave? 4F1, that would be a doubling, right? When's the next octave? 8F1, right? So now, and then the next one would be 16F1, right? So as you go up in octaves, the partials that fit, the number of partials that fit in that octave, they get to be more and more and more and more. Right? So there's a lot more flexibility on the fingering you can use to get the note as you go higher. Do you have anything you can show some of that? Yeah, okay. Sound good. So we'll come back to that thought. But here, let's do the mute while you've got the trumpet.
Oh,
Do the mute while you've got the trumpet.
So there's like tons of different trumpet mutes. Street mute is most common, basically just like makes it quieter. There's a bunch of different ones, and basically the idea is that it's like your vocal tracks. Like this, the sound is going to stay the same, but it's going to modify how the sound is. So you have your regular. And then
So can you see how it brought out different partials, right? That where the lines are didn't change because that's controlled by the lips, right? The source, right? The area of the lips. But just like formants, like there's less energy at that partial, but more energy in these partials. Just like the formants shifted around where the energy was. That's what the mutes are. It's that same one.
I don't have a plunger mute, but you can use your hands for basically the same effect.
And that's a little bit like a vibrato because it has kind of that oscillation in pitch, right? So that's kind of, and why would it change pitch? Because the length is changing, right? The length for those standing waves is changing. French horns players use that a lot. Anybody in here ever played French horn? So the hand, this other hand is like always doing interesting things, right? And it's all of that idea of getting exactly the right length to get the mode shapes you want to end. There you go. Okay. All right. You can switch to the baritone is sort of more regular instrument, right? No?
I've got a piece of my bass player.
Bass clarinet is her regular instrument. Okay.
But I do that easy. Yeah. Okay.
Okay. So she can play all sorts of things. So we're very grateful that she's playing brass. Okay, so why don't you just go ahead, first, tell us how you play different notes with keys. Tell us how the keys
Okay,
work.
yeah, so basically, these 3 valves, 1, 2, 3, and you can see there's a little like bit of tubing attached to each one. This was attached to the first one, that brings it down a half step, and then this tubing is a little longer, brings it down a full step, and then this tube right there is a little breaks it down 3 half steps. So in order to get a full range of notes between like F2 and F3, you can't develop them down F1. Then like you bring it down a half step, down a whole step, and down 3. This goes down 4, 5, 6, 7, 8, and then down to the next one. And then as you go up partials, it takes fewer steps to get it to each one, so you use less of the vowel combinations as you go. But eventually you get a point where you can just kind of do whatever you want. I'm not there, but you can.
Partials are also close together. It close together in the terms of how many fit in an octave. Right? Because in the first octave, say from 2F1 to 4F1, there would just be one in there. But then from 4F1, so up to 8F1, you've got 3 partials in that. The next one you have 7 partials in that, which is almost all of the notes, whole notes. So that's how that. Okay, good. So why don't you go ahead and just play a scale for us, so we can watch the sound and then watch your fingers. All right, thank you. What do you notice about that spectrum? That's a lot of energy here in these low frequencies, right? And then you've got F1, 2, F1, 3, F1, 4, F1, 5, F1, 6, 7, 8, 9, 10. You still have about 10. They're just not spread out as much, right? Because F1 is so much. So how would you describe that sound compared to the trumpet sound? We've used the word warm, right, or mellow. Okay, so those words mean low frequency content, whereas bright, which is the word we usually use for trumpet, corresponds to all these extra high frequencies.
This is probably a really dumb question, but so if your lips can change the fundamental frequency, could your lips hit all of those as well? Like,
Yeah, if you have just a mouthpiece, it's just the tube that like suggests to your lips like we're supposed to be easiest to hit. You can pitch bend like a little bit around the note that the tube is that makes sense with the tube length, but it's really
So yeah, that's a really good demo. So with the mouthpiece. Okay, so let's go ahead now and do the just a favorite note, and let's do soft to loud. Okay, so what do we notice? Loud, soft sounds versus loud sounds with the spectrum.
higher partials.
So you get more energy in the high frequency partials when you play loud. Okay, that's going to be a theme every single day in our music. Okay, why? What is it that makes more high frequency partials when a loud sound is being played? More energy, okay? Right, more energy from the air. And as you saw in that trombone lip video, that makes the lips open and close wider, right? And there's a more abrupt motion, which means that the corresponding airflow, right, instead of being something like this when you're playing soft notes, becomes something more like this when you're playing loud notes. And the more peaked or sharp bends you have in your sound, the more high frequencies that corresponds to. More high frequencies. Questions? Okay. Let's go ahead and have you on a single note again play partials. So one you're open to, if you could just take.
so maybe
If you can. Okay, so here you see this first one here, with F1, 2F1, 3F1, 4F1, 5F1, 6F1, all the way up, right? Okay, even multiple. Now when she hits the next note, okay, this partial is excited, that partial is excited, that one is excited, that one is excited. So it skips every other one, right? Because the new fundamental is step one, pedal tone. And so it's then twice that, 3 times that, 4 times that. You skip. And then the next one, right? When you do 3, then you're doing 3 times the pedal tone, 6 times the pedal tone, 9 times the pedal tone, 12 times the pedal tone. But that's the same as this one, 2 times that one, 3 times that one, 4 times that one. So you're accessing your spectrum of your sound is a combination of different partials that exist for that tube. Okay, so one example of that, okay, if I have, let's say, pedal tone, we'll just do hundreds because we can find it some other than what's on your sheet. Okay. We'll do 50. Let's say you have really long tubing, so your lowest note you could play was 50. That means that that tube length could support all of the multiples of 50, right? Now, if you change your embouchure, how the lips are buzzing, such that you're playing 150 hertz. Okay. Which of these partials are going to be present in the spectrum? This is how you're buzzing your lips. 150 times per second. That's the pitch that's being heard. Which of all of these partials supported by the tube are going to appear in the spectrum? Multiples of 150. Those are the ones that will actually be lit up in the spectrum. Even though all those other resonances of the tube exist, once you get your embouchure set on the pitch you're going to play, it's multiples of that pitch that will actually appear in the spectrum. Questions about that?
So on wood rings, the lower notes or the quieter notes, something like that.
So you have a little bit of how with like when you go up to a higher octave, there's more like partials and so with the spectrogram, I don't understand because it looks like the lower note, it looks like they were all close together, and the higher that it got, the further apart they got from each other. So I don't understand how that.
So for this specific case, right? This is one octave. Okay. This tube length. This would be an octave. This would be an octave. This would be an octave. 50 times 2 is 100. 100 times 2 gives me 200. 200 times 2 gives me 400, right? And then it would be all the way up to 800. That would be my next octave. So the possible partials that you could choose as the pitch increases. Right? This octave is 1 octave. There's nothing here. You could, in this octave you have 3 choices for what pitch you could play. And in this octave you have like, four extras, and then this one you have 7. Does that help? Write it down, write it down. Okay, so all right. You want to play some questions?
I don't. But I have the mouthpiece.
Oh, yes, okay. So then the other thing is the impact of the mouthpiece on the sound. Okay. I'll let you talk about how those are and what they do and how to choose. Oh, yes.
So yeah, so this is another version of the mouthpiece. It's a little the cup of the mouthpiece is a little more shallow, and so it makes a brighter sound and it's easier to hit the high notes. So this is what this one sounds like. It's a little brighter sound than the high notes. The high notes are a little brassier. And they're easier to hit. It's not that much of a sound difference, but you can turn the mouthpiece and just it makes a whole different sound, and it sounds a lot more like a trumpet. But my favorite thing to do is you take a clarinet mouthpiece and you stick it on the trumpet. That sounds like a saxophone. The like notes are a little weird because that can actually play like really. It's kind of funky, but because it has the more conical tubing for some of it, like a saxophone would, and it has a different kind of oscillator, then it will sound more like a saxophone.
Interesting. Thank you very much. Thank you very much for doing it. So much better to like see it in real life. Okay, so number 5 on the back side. Okay, so number 5. Well, we're just talking about here. If the first 10 modes of a lit reed instrument are, based on the length of this list, 105 on up. Okay, and then if the note you played has a fundamental frequency or pitch of 315, which of these partials will contribute, meaning they'll show up in the spectrum? The answer is C. So if you didn't know that, ask me questions so you can make sure we're all on the same page.
This is a marching baritone, and so you're not going to see this in concert, you're going to see mostly a euphonium, and it's the same range, it's slightly different pitch, not pitch, slightly different timbre, it's a little different. So don't.
And it points upward like a tube.
Yeah, it looks like a really well, I suppose. It's more difficult to march.
In marching, right, you want your radiator pointed to the audience, right? Because you're out in the open and there's no reflections, send that sound to your audience. That's why it's going to marching band point forward, the baritone to marching band point forward. But in a concert, right, it's more convenient, easier on your arms and everything to set it on your lap. The sound will go up because it can then reflect off the screen or the band. It's all about that.
Yeah, I was just gonna ask about, this saying that 6:30 and 9:45 should be 2:15, is that what it's asking?
Yes. So that's saying if the tube length had all of these numbers, 105, 210, 315, et cetera, and but you chose your embouchure to play the pitch of 315 and you looked at the spectrum, you would only see 315 and multiples of 315. So all of this list is the tube resonance list. Once you choose the pitch, you determine which partials will light up in the spectrum.
And you may have already explained this. So why wouldn't 105 be on that list as well?
Okay, because the fundamental frequency is the lowest partial that it's accessed.
Okay, thank you.
The pitch is the lowest note that will show up on your spectrum. And there will be multiples of that one that will show up on the spectrum, which means they are part of that sound.
Thank you.
Other questions? I should say it's more ways. Okay. Okay, let's see, number 5, we listened to that, okay? Let's just see how well you remember. So question number 3, under Roman numeral number 5. When a recording of a tuba is played twice as fast as it was recorded, what is it going to sound like? Trombone. And when a recording of a trumpet is played half as fast as it was recorded, what will it sound like? Have any of you played with music and like tried to adjust the tempo without adjusting the pitch? Electronic music thing? Yeah. You have observation about that?
Yeah, there's certain like ways to go about doing it, and like if you do it the wrong way, then it'll basically speed up. So it's the tempo and make it and like just like it's right up.
Exactly. So in some in Audacity, which I think you played with me last week, there's a change tempo and a change speed. The change tempo preserves the frequency that just increases the tempo, but change speed changes the whole time axis, which then shifts the frequency. So that's one thing. Okay, good. Oh, while we're on this side, let's do Roman numeral number 7. Okay. What mechanism causes a flute, clarinet, trumpet? So we're on trumpet today. To sound a note an octave higher. So to go from the F F1 to 2F1, to jump that octave. What is it that they're changing? The embouchure, so it's the tightening the lips, just here on your little cheek.
How do you spell embouchure?
So EMB, I'll write up. This is right. Correctly, it's wrong.
So close.
Is that correct? Must be French. French. Okay. All right. Okay, so now we come to Roman numeral number 3. We talked about the relative strengths of high and low frequency energy, and it's going loudly and softly. Are there any questions about that one? Loud sounds versus soft sounds. Okay. Now this next part is not on your test, but it is on your homework. So we're going to spend a little time thinking about it. It's a little bit more complicated, but an interesting one. And this is for all of these students. Just draw. You may not know, with the trombone, there is a slide that they move with their arm to change the length. All the other brass instruments have valves. They push the move. The trombone is the one where you change the slide and valve. Okay, so let's say this is length L, where the bell starts. And then you've got the bell, right? So now you have longer than that, right? Some little extra length so that the effective length is long. Now, what we mean by that is that if we draw our mode shapes, okay, they don't end right there. They end a little bit farther into the bell. Okay. So the effective length of the instrument is telling you about where the mode ends, where that last note will be. Okay. There versus a little bit of extra length. Okay? So where that mode shape actually ends is inside the bell. And because of that, that's one of the effects of the bell that makes it brighter, pushes those partials closer together so you have all the harmonic partials. All right, now the thing you have to understand here is the sound we hear is the sound that's leaking out of the sound that's making a standing wave. Okay, so to set up the resonance, you have to have the sound going there and being reflected back, right? It's that interference pattern of the direct down, the left and the right pattern makes this wave. So for that to happen, there has to be a reflection here. And that reflection will only happen for those resonances of the two, those certain frequencies. But we're not actually hearing the sound inside, right? We're hearing the amount of that sound, those frequencies that leak out of. So one way to identify modes is to look at the power of this reflection, the strength of this reflection. So when you see the power reflection coefficient, that means how much of that is back into that. So most of the pictures in these music chapters, instead of having a spectrum, they actually have this power reflection coefficient. Okay. Which has peaks like this. Basically saying these are the frequencies at which there's a lot of power reflected so they can actually support standing waves inside. Okay, so the power reflection coefficient in general decreases as you go up in frequency. Okay, but because it's reflecting less of that power, okay, that means that more of it escapes to the higher frequencies. So higher frequency sounds will have B, relatively greater high frequency. And it also limits the number of harmonics. There is a point above which you don't get enough reflection back. So B and C are the correct. Without even primarily clear homework, that's not something to test on, but. Okay, any other questions about our listening family? Okay, we'll do Aerojet next time. If they want to-